did you want to say something? Okay, so welcome to STEM Talk, the Thursday version of STEM Talk Week. I'm going to talk about what's called population 3 stars, the first stars that ever existed in the universe. The sun and the solar system are only about a third as old as the whole universe. And that's probably couldn't be any other way that we could live on a planet orbiting a star that's only a third the age of the whole universe, because there's strong evidence that at the beginning of the universe, only 2 elements existed, hydrogen and helium. And all the other elements are thought to be generated by nuclear processes associated with stars. So stars had to form and exist, and there have been many generations of stars that have existed prior to the existence of the solar system. And so the first generation of stars formed from only hydrogen and helium, from pure hydrogen and helium, but nobody's ever observed any yet. And I want to talk a little bit about why and how to observe them. So if you look at the spectrum of the sun, that's on top, these are the small section of the spectra of several stars, the sun and 3 other stars. So this is wavelength on the horizontal axis. So what that line indicates is how bright the sun is at all these various wavelengths. And you can see there are these dips where the sun, at particular wavelengths where the sun is not as bright. For example, right around, what would this be, 5184 angstrom units. The sun is not as bright, and each of those dips, those features, is associated with an element in the atmosphere of the sun. And you can see some of these are identified, like titanium gives rise to that feature, iron to that feature, chromium to these 3, in all 3 of these stars, magnesium to these 2, and so forth. So all these features are due to some element. And you can see that in the sun spectrum, those features are relatively strong. That's because the sun has a good bit of those elements other than hydrogen and helium. And when people first started to look at stellar spectra, this is what they saw, these strong features due to all the other elements other than hydrogen and helium. And but then eventually they found stars with relatively weak features in their spectra. You can see these are weaker than the sun's features, and this one particularly weak. And that's because these stars don't have as much of that stuff. They are closer to being pure hydrogen and helium. And so they separated stars into 2 populations, population 1 that are like the sun, population 2 with these weaker features. It turns out that these stars are systematically older than the sun, and so they formed at a period in the history of the universe when it was closer to being pure hydrogen and helium. It had not been enriched as much in the elements other than hydrogen and helium because there hadn't been as many generations of stars to produce those elements. So, so you might guess, well, the first generation of stars formed from just hydrogen and helium, so they shouldn't have any of these features at all. You would see only features due to hydrogen and helium. But nobody's ever seen a star like that. So these have been called population 3 stars. The first generation of stars were made of pure hydrogen and helium. So why don't we see these stars? Well, as we'll see, it's probably because these stars are all gone now. They have lived, they formed and went through their whole lives and have already burnt out. So that's probably why we don't see them. And we'll see that they were probably quite different from the stars today because of the fact that they formed from just hydrogen and helium. So let me go through a brief history of time here. This diagram is supposed to represent the history of the universe, and the widening toward the right is supposed to be the expansion of the space of the universe. The universe is 3-dimensional, but this would be like a 2-dimensional. So every slice this way is like a 2-dimensional universe expanding. So there's the Big Bang, and there was furious expansion, and then it's been expanding at a slower rate for most of the history of the universe. And here we are out here at the present day. Now, another thing that this diagram nicely illustrates is the notion of look-back time. Light has a finite speed, so if you look at an object that's a distant object, you see it as it was in the past, right? If you look at an object that's a million light years away, you see it as it was a million years ago. And if you look at an object a billion light years away, you see it as it was a billion years ago. So if we can look far enough away in space, we can see all the way back to this first generation of stars. And it's right here where the stars began to form. And in fact, we already have light that comes from further away than that. This is the cosmic background radiation. This is a full sky map of what's called the cosmic background radiation. This is from a period in the history of the universe. The space of the universe was expanding. At first, all the stuff of the universe was compacted into a very small space, so it was very dense and hot. As it expanded, the temperature dropped, and eventually atoms were able to form. Prior to that time, the electrons couldn't go into orbit around the nuclei because the temperature was too high, and they'd get kicked right back out. But when the temperature dropped low enough, atoms formed. At that time, the universe became essentially transparent, and the luminous energy that existed at that time, we can still see that today, and that's the cosmic background radiation. And this is a map of that. Now, that radiation is almost completely isotropic across the sky. These color variations represent very, very slight deviations in the temperature from one spot to the next. They're enhanced because these are very important deviations. They represent where matter was slightly more dense, but it's only like 1 part in 100,000 difference. In other words, matter was distributed very evenly at this point. It was just a warm gas that all the matter in the universe was composed of. And that is at this point right here. Okay, so here's the Big Bang, luminous universe. This is where it became transparent. And so matter is distributed very evenly at this point. And then gravity, during this time, gravity is causing these deviations in the density to amplify so that matter began to clump and eventually could form stars. This they call the cosmic dark ages. If the universe is luminous here, it cooled down, became non-luminous, and before any stars formed, it would have appeared dark to human eyes. I mean, there was still radiation like infrared, but it would have appeared dark to human eyes. And then when stars began to form, when it was sufficiently clumped where stars could form, then visible light was created again, and the universe was relit in the visible part of the spectrum. So here's the first stars, and then these stars formed in large groups and merged together into galaxies, which merged into larger galaxies, and we have the progression toward today. So it's these first stars that we're talking about. So to observe them, none exist today, evidently. So to observe them, you've got to look at these huge distances away, huge look-back time. Does that make sense? The further away we look, the further back in time we can see. But to see the first stars is particularly difficult. So to talk about how these first stars were different, let me zoom ahead and talk about the composition of the solar system in terms of the elements. So here's a pie chart of the elemental abundances in the solar system, and the top of the chart, the top of the chart is, you don't see it, but the biggest piece of pie is hydrogen. It starts there at helium, but anyway, this hydrogen, helium, third one's oxygen. So the point I'm trying to make with this is the most abundant elements by far are still hydrogen and helium. Those are the ones that existed at the beginning of the universe. They are still by far the most abundant elements. But the material now, the material of the solar system, has been enriched in the other elements, the other 90 elements that we have on the periodic table. But they're all stuffed inside this little section of this pie. And those elements make a big difference. Life on Earth is dependent on like several dozen elements, right? So that's one of the differences it makes. Here, I'm showing the same data in a little bit different way. The orange bars have excluded hydrogen and helium. The orange bars are the 8 next most abundant elements in the solar system. So oxygen is number 3, then carbon, neon, iron, nitrogen, silicon, magnesium, sulfur, and so forth down to the rarest elements, which are billions of times less abundant than these. So this is, the orange bars are solar system abundances. The blue bars are the predicted output of groups of heavy stars. It's these really heavy stars that have these nuclear processes going on inside them, which produce elements. And it's actually possible. People have been simulating what goes on inside these heavy stars for many decades now. And with these models, they can actually mimic quite closely the elemental abundances of the solar system, not only for these 8 elements, but for essentially the entire periodic table. So this appears to be where the elements come from, these nuclear processes in stars, because the predicted outputs is very close to the same. Let me go a step further and show you the abundances in the Earth. So this is the whole volume of the Earth. I'm not showing, this is not simulations now, this is just abundances in the Earth. And you can see that iron is the most abundant element in the Earth, because the whole core of the Earth is iron, and then oxygen, silicon, magnesium. These 4 elements are responsible for like 96% of the mass of the Earth. Let me go one step further and show you the crust of the Earth, its abundances. And so oxygen and silicon, that probably doesn't surprise geologists, and silicon dioxide is the basis of many important minerals. And then you can see how the elements rank in abundance of the first few. You know, the rest of the periodic table is out there somewhere. So these elements are obviously very important to us. I mean, there's something like 25 elements in our physiology that are functional in our physiology. And so life couldn't exist without them. So that's why we're standing on a planet orbiting a relative latecomer star, because these elements exist here. But these elements also have a strong influence on the formation of stars. And that causes star formation in the present universe to be quite different from the first star formation that ever occurred. And they affect it through these little critters. This is an interstellar dust grain. Microscopic, it's an electron micrograph, but this is an object from outside the solar system collected by a spacecraft. And it's made of, most likely made of these elements other than hydrogen and helium. So oxides and aromatics, rings of carbon atoms with hydrogens, graphite. This is thought to be what interstellar dust is primarily composed of, and it's these elements other than hydrogen and helium. Now this stuff, there's quite a bit of interstellar dust in our galaxy, probably hundreds of times the mass of the sun, and it's important in star formation because of the way it emits light. Solid objects emit light differently than do gases. And this is the emission spectrum of interstellar dust. It's a broad spectrum, goes way out into the infrared part of the spectrum. That's important in star formation because stars form from the clumping of gas. Gravity brings clumps of gas together where it's more dense, it comes together, and you can form a star. But as stars form, as the gas comes together by gravity, energy has to be released, right? This has potential energy in it, right? If I let it go, energy is released. It made some sound, it made some heat there, but energy is a conserved quantity of it. And extend that to a whole star, as this stuff comes together, there's a huge amount of energy that has to be released, or it can't continue to compress, right? How is that energy getting out of there? Well, if there's dust in it, that provides a very effective mechanism for cooling the material, because the dust emits wavelengths, long wavelengths, which can make their way through even these relatively dense clumps of gas in the interstellar medium. So dust provides an efficient cooling mechanism so that these regions can form stars. And the effect that has on stars is seen through this equation. This is called the Jeans radius. And let's say this is an idealized situation where you have an isolated spherical region of gas in space of homogeneous density, and there's two forces acting on the gas. Gravity is trying to make it come together. Its whole self-gravity is trying to make it come together to form a star. But there's also gas pressure, which is trying to keep it from doing that. Which one's going to win? Well, if it's bigger than this radius, then gravity will win. If it's smaller than that radius, then gas pressure will win and it won't collapse. And you can see it's dependent on several factors. Now that's a constant, the gravitational constant. That's another constant of physics. This is just the average mass of a gas particle, which doesn't vary much from one gas cloud to the next. But this is the density of the stuff. You know, the number of kilograms per cubic meter, the density of that. The higher the density, the stronger gravity is, and the smaller that has to be, the smaller the cloud has to be in order for gravity to be strong enough to collapse it, right? So the more dense it is, the smaller the cloud can be and still collapse. But the higher the temperature, the greater the gas pressure, so the larger the cloud has to be in order to collapse. So if there's dust in it, the dust can effectively cool the gas in there by this infrared radiation that it produces and decrease the minimum size of the gas cloud that can collapse. And you can get smaller stars. So the masses of the stars that form depend on how well it can cool itself. And if there's dust in there, you can get smaller stars. So the stars that form today, which contain lots of dust because there have been previous generations of stars producing these elements of which the dust is made, the stars that form today are, on average, much lower in mass than the original stars. And that has a strong effect on, here is, this blue line is what's called the initial mass function. When stars form in our neighborhood of the galaxy today, what masses of stars that you get? This is one solar mass, the same as the mass of the sun. It turns out that it's right at the peak. A lot of mass goes into stars, the same mass as the sun. Not as much mass in heavier stars, not as much mass in lighter stars. These lighter stars are actually more, this is a tenth the mass of the sun. These lower mass stars are actually more abundant in number. There's more of them, but each contains less mass, so the total amount of mass in them is smaller. So there's more of them, but this is, in other words, this is where the mass goes in terms of the masses of stars that form. But here is one model of the of star formation from just hydrogen and helium. It's much heavier stars. And this I actually got from a paper that is quite optimistic about lower mass stars forming. It has to do with, well, what are the cooling mechanisms that can cool the gas? And this proposes that molecular hydrogen could cool the gas. But if molecular hydrogen didn't exist, then this would be shifted toward much higher masses. And most astrophysicists think that the first generation of stars probably were hundreds of times the mass of the sun, maybe even thousands of times the mass of the sun. So I didn't probably explain well that this number, solar masses, this means stars 10 times the mass of the sun, 100 times the mass of the sun, and so forth. So if that's the case, I mean, we don't know where this curve was for the original stars because we don't see any of them, and we'd have to look at these enormous look-back times in order to directly observe them. But it's an important question because, oh yes, one of the parameters of a star that is affected by its mass is how long it lives. The heavier stars don't live as long because they burn their fuel faster. So a 100 solar mass star only lives about 100,000 years. So this is the lifetime of the star, the mass of the star. And even a 10 solar mass star, 10 times the mass of the sun, is gone before 50 million years is up. So if the lowest mass stars that formed from the original, from the first generation stars, if the lowest mass stars are 10 solar masses, they are long gone because 50 million years is a tiny fraction of the age of the universe. So this is a adequate explanation for why we don't see any of these populations of these stars. They were all huge because they formed from just hydrogen and helium, so only big stars could form because of this cooling problem. And big stars don't have long lifetimes, they're all burnt out. So that probably explains why we don't see any today. But these super heavy stars have interesting implications for the evolution of the universe, because, again, here's solar masses, and this is the mass of the remnant that they leave after they're dead. So the red line is the mass of whatever compact object is left behind. So the sun, when it burns out, it'll leave, we think, an object called a white dwarf, which is a very dense, small object that'll probably have half to 60% the mass of the sun. And here's one solar mass. The red line doesn't go down that far, but it goes way down here somewhere. But you can see a 3 solar mass star will leave something more like 0.7 or 0.8 times the mass of the sun. And the heavier the star, the heavier the remnant that it'll leave. There's only so heavy a white dwarf can be, for reasons having to do with relativity, and heavier than that, it'll collapse into what's called a neutron star, which is sort of like an enormous atomic nucleus. And so stars from, 8 maybe on up, they leave neutron stars, and we observe many of these in the galaxy. Heavier the star, the heavier the neutron star. There's only so heavy a neutron star can be, and it'll collapse into an even denser object called a black hole. So from here on up, which is probably 20 to 25 solar masses, the stars are thought to be just black holes. And the heavier the star, the heavier the black hole that it'll leave. So if there were 1,000 solar mass stars, and these computations are done for zero metallicity, which means pure hydrogen and helium, they would leave an object that's close to the total mass of the star, a black hole. So it makes a difference which of these stars, where that initial mass function was. In other words, how many of the stars of various masses were produced in that first generation, because they would have produced a very large number of these pretty heavy black holes. Interestingly, there's this range here. Now this graph is highly theoretical, because it's very difficult to tell. We see black holes and neutron stars and white dwarfs in space. Very difficult to tell what stars they came from, right? But so this is highly theoretical, including this part. It's thought that stars between about 120 solar masses and 270 have a special kind of supernova explosion when they die that leaves no black hole, leaves no remnants at all. It's a big thermonuclear blast that just produces a whole lot of elements. So if that's true, and if the first generation stars included a lot of those, then there was a very large production of elements and a very large production of black holes, very quickly, early in the history of the universe. So we do know that this is some of the most distant objects we can see are quasars. So this fuzzball is an extremely distant quasar. That's something closer. It's not nearly as luminous as this thing, but it's just much closer. So we're seeing this as it was when the universe was only 770 million years old. Now it's almost 14 billion years old. So we're seeing this at a very large look-back time. And these quasars are powered by supermassive black holes that are billions of times the mass of the sun. And the presumption is that these extremely large black holes form from the coalescence of many of these smaller black holes, like the hundreds of solar mass black holes that might have emerged from these first generation stars. And we know that these were formed relatively early on, so this thing already existed in the form in which we see it 770 million years into the history of the universe. I mean, it's a long time, but that's it's only about 6% of the age of the universe, right? So when the universe is only 6% of its present age, it had already cranked out a bunch of black holes. They had coalesced and formed the supermassive black hole that's powering this object. And there are lots of those, even at these really large look-back times. That's just an artist's conception of stuff orbiting a supermassive black hole. We also see extremely distant galaxies at these very large look-back times. This is this little smudge in here. You can't even hardly see it there, but it's blown up. This is a galaxy. In other words, this is starlight. and we're seeing it as it was when the universe was 500 million years old. So this is a very early galaxy, one of the earliest known. These other galaxies this is a star in our own galaxy, very, very much closer than these other things. But these are nearby galaxies. Here's another one that's even fainter and maybe further away, but this one is controversial. It may actually be a closer object. This is a very important one. They just call it CR7, and we're seeing it as it was when the universe was a little bit older, 870 million years. But it's very luminous. It's unusually bright for these extremely distant galaxies. And that makes it possible to do some crude spectroscopic analysis of it. Make a spectrum to see what the stars that are emitting the light, what they're made of, right? And the people that have done this research say there are patches on this galaxy in which they can see no evidence for the features due to elements other than hydrogen and helium. So this is consistent. It's extremely distant. I mean, you can see how blurry this thing is just because it's so far away. It's very difficult spectroscopic work to do, but they say their results are consistent with at least patches of this being composed of stars that are made of pure hydrogen and helium. So this may be the first observation of population 3 stars. And from this kind of work and looking for galaxies at deeper and deeper distances away, this graph has been made. It's an estimate of the star formation rate as a function of time in the history of the universe. So the time axis is at the top. That means 400 million years, 600 million, a billion, 2 billion, 3, 4, 5, 10, and we're out here somewhere. So the star formation rate picked up and went way up, peaked out at maybe 2.5 billion years into the universe, and it has been decreasing ever since. So this graph has a bit of an odd axis, but what I've done is I've taken points off of this fit curve and I've made a more viewable graph. So here we go. Here's the beginning of the universe, and these are billions of years. So we're just off the end of this axis here at the present day. So the star formation picked up, peaked out at 2.5 billion years, and has been decreasing like this. So this is based on these on numerous studies of looking at galaxies at further and further distances away, and looking at studies of star formation over the history of the universe, over these range of large look-back times. The sun formed about right in here. So the solar system really is a latecomer in the history of the universe. You can see that most of the star formation activity had already occurred by the time the sun formed, and more than 90% of the stars that had formed, or not more than 90% of the mass that had been involved in star formation, had already done that by the time the solar system formed. So we really are kind of a latecomer. So, so how do we study these things? Well, if all we're left with is to look at these enormous look-back times, then it would help to have fancier telescopes that can see in more detail these extremely distant objects. And one that's being developed now, it's being tested now, this is the James Webb telescope, the successor of the Hubble Space Telescope. So this will fly in space, as you see in this artist's conception. And this big thing is the mirror that'll do the focusing of the light. This is a mock-up of it to show you the scale. And I guess these are people involved in its development. The Hubble mirror is probably about that big. So it's a much larger mirror, much more sensitive. In other words, it'll be able to detect fainter sources of light and resolve them better angular resolution. And it's essentially an infrared telescope. This shows so this set of points represents how sensitive Hubble is in different wavelengths. Okay, this is like the visible part of the spectrum in here. So it primarily looks at things in the part of the spectrum that our eyes can see, but it extends into the infrared. This is the James Webb telescope, extends way further into the infrared, which is actually quite helpful for looking at these extremely distant objects, because there's more infrared coming from them, and probably more diagnostic of the things that are going on with them. These other instruments are presently existing instruments like this. The Spitzer infrared telescope is in space, and it's made all kinds of cool discoveries on stars and some of these deep sky objects. But you can see that the further down the points are, the more sensitive those telescopes are. So this takes it down to more sensitive. There are other telescopes being developed. This is an artist's conception of the ELT, the European Extremely Large Telescope. And this is a pickup truck. And this is they're now preparing the site for this in the Andes Mountains. It's one of all the observing sites in the world. This has some of the driest air. The water interferes with observations of the atmosphere. But this is the telescope. See, these are people, and this is the mirror. It's a 39-meter optical telescope, which is way larger than any optical telescope that presently exists. By optical telescope, I mean this will view in the part of the spectrum that we can see, and further than that in other parts of the spectrum as well. But this is way more sensitive than telescopes that exist today. And although it will have to look through the atmosphere, unlike the James Webb, which will be in space, this telescope will have to peer through the atmosphere, which degrades your view of what you're looking at. It'll have all the latest adaptive optics, which is there's all these little sophisticated motors on the parts of the mirror that very subtly change the shape of it to undo some of the effects of the Earth's atmosphere that blur our view of what we're looking at. So in some ways, it'll be almost like this thing is in space, and we'll have a clearer view of it. So a telescope like this is extremely valuable for all sorts of stuff. I mean, they'll be able to directly observe planets orbiting nearby stars, make detailed objects of really faint objects in the solar system, some of these real faint objects that are in the outer solar system, and of course look at these extremely distant stars. So this will be finished within 8 years, I think. So already had the funding procured. So here, this is just a comparison of mirrors and some of these. Here's a person. Here's the EELT. They're building another huge telescope in Hawaii. I'm not sure what the progress is on that. But these are some of the other. The Keck telescope at the top, that's in Hawaii. And some of these others are presently existing very large telescopes. Here's James Webb. This will be in space, of course, which gives it a great advantage. There's the Hubble mirror. When I was a kid, see that Hale right there? That was the super telescope that was built in 1950. And that was pretty amazing back then. But in the 1980s, people figured out how to make telescope mirrors in segments and bring them to the site and assemble them there and still make them optically perfect. So the original one that they wanted to build, the Europeans, is this thing. See this? That is the overwhelmingly large telescope. But it was canceled because it turned out to be overwhelmingly expensive and complicated to build, and they weren't even sure they could make it work right, being that big. So, but anyway, they ratcheted back to this, which is still pretty amazing. So, with these, yeah, that's Arecibo. The Arecibo radio, yeah, you can't. Yeah. Arecibo, that's the world's largest radio telescope. The longer the wavelengths, the easier it is to focus the light. And so there's a 1,000-foot diameter radio telescope in the hills of Puerto Rico. And it's the most sensitive radio telescope by far in the world. So yeah, that's this is a tennis court. There's a basketball court. I'm sorry? See this? Oh, 1,000 feet. Arecibo is about 1,000 feet across. You've probably seen pictures of it. This huge dish that's sort of nestled into the hills in Puerto Rico. Okay. So what about sort of these huge telescopes will come online within 10 years and we'll be able to see deeper into the universe. But what else can be observed to study the early universe and these first-generation stars? Well, here's what the stars, they first formed here. What about the dark ages themselves? So this is, to remind you, this is when the universe became transparent. This is where we see the cosmic background radiation. And then between here and the formation of the first stars, gravity was bringing this stuff together, beginning to clump the matter so that stars could form. Is there any way to observe that material? Well, radio astronomers in the present universe routinely observe other galaxies with radio telescopes because atomic hydrogen, the most abundant element back then, emits a particular radio frequency, about 14.5 gigahertz, because of an interaction between a magnetic interaction between the electron and the proton in a hydrogen atom. And so that's the way they map atomic hydrogen in relatively nearby galaxies. Is it possible to use radio telescopes to map the atomic hydrogen back here? Well, yes, but it's not easy because the universe has been expanding ever since then, and it's increased the wavelength of that light, and it's decreased the frequency all the way from 14 gigahertz down into the like 10 to a few hundred megahertz range. And that's right in an area of the spectrum where we do a lot of communicating. When you tune into 95.7 FM, you're tuning into 95.7 megahertz radiation produced at 50,000 watts by some tower downtown. So the Earth is a luminous source of radiation in that whole waveband. And of course, it's not just FM radio. It's TV and AM and cell phone and all this communication stuff where we create a lot of radio energy. It's pretty well impossible to observe the subtle radio signal from this extremely early part of the universe from the surface of the Earth. And it's probably impossible to do it from the space near the Earth. But there is one place that's relatively close by where it is possible, and that is the far side of the moon. The moon is facing us with the same side, so as I go around, I see the same side of this eraser, right? We call it synchronous rotation, so that the far side is always facing away, and it's a very radio quiet place, even though the Earth is this very bright source of radiant energy. The far side of the moon is a very radio quiet place. And the moon is also a very stable object. It's tectonically almost not active at all. There's almost no moonquakes there. So it's a good place to build the astronomical telescope and observe the universe. And of course, it has no atmosphere, essentially. And so you don't have to look through an atmosphere. The only problem is it's the far side of the moon. And, is it really conceivable that we could build a sophisticated radio telescope to observe at these distances? Well, engineers have done studies of this very thing, and they say it is possible, although it would be very difficult. And the idea is you land, this is done robotically, you land a robotic lander on the surface which has these robotic rovers, and they run around and they deploy these arrays of antennae. Each of these things is a radio antenna, and this is like an unfurlable, some sort of mylar sheet which is unfurled by these rovers around, zooming around. And they have literally hundreds of these arrays spread over an area at least 10 kilometers in diameter. It has to be big like that because this instrument would be acting like a very large radio telescope to resolve things at a super large distances, right? So it would have to be over a large area. So a very ambitious project if it would be done, but people keep talking about this project, and you get enough countries together and enough interest in this sort of thing, and you can actually pull off these ambitious projects. This lander is actually was designed for, well, about 10 years ago. NASA was interested in doing more, building a lunar base, so they needed to land people and stuff, and that was the descent stage for that. So, you know, if they build that, it could also be used for human exploration, and there are a number of countries that still want to do human exploration, so at least the hardware could be used for both ambitious robotic missions like this and also manned exploration. And the idea, which you observe, so okay, here's what we're trying to look at: the hydrogen in this extremely early time, the dark ages. We want to see what it's doing, how it's clumping together to form stars. But the oldest radiation comes from this moment, which is about 380,000 years after the beginning. This is when the atoms formed. That light is coming through this stuff. And what they would actually observe, according to these engineers, here is the spectrum of the cosmic background radiation. That's observed with a whole bunch of different instruments now. In the very low frequency end of this spectrum, you'd see this feature would be superimposed on the cosmic background radiation. In other words, it's like an absorption feature, like those features in the spectrum of the sun. That would be due to this material in front of that affected this spectrum after it was produced. And they say that this feature indicates what we would see if the gas is coming together to form stars, and then this little spike is due to when the first stars light up and they interact with their environment and produce a feature something like that. So these features would indicate when star formation occurred, the first star formation in a particular line of sight. And the idea being, you choose all these different lines of sight and map when the star formation occurred. The frequency that this appears at determines when it occurred, because as the universe expands, the frequency of a particular radiation drops. So the more it goes down this way, the later it occurred. I don't know if that makes sense, but by seeing where this feature occurs on the spectrum, you can tell when stars first formed at those locations. So here's the radio astronomy version of observing the first generation of stars. You're not directly observing the stars at all, but you're observing their interaction with the environment around them. So this is one of the reasons this is important, is because the cosmologists tell us there's more we could learn about the basic physics of the universe from studying the very early universe than we already know. I mean, we know there's things about the physics of this universe that we don't understand, like the dark matter. Most of the mass in the universe is in a form that we don't even know what it is. I mean, we really have very little idea. There's all kinds of speculation, but nobody's ever directly observed it. So what is that stuff? And then there's this dark energy out there that's making the universe accelerate in its expansion. We don't know what that is earlier. Part of this effort to explore the early universe and what was going on is an effort to understand those things, basic physics of the universe. And when you understand basic physics better, you never know what kind of Star Trek-y technologies you can come up with as a result of knowing more about the basic physics of the universe. So, anyway, this may be where the research goes, but we'll certainly know more about population 3 stars due to these enormous telescopes over the next 10 years or so. So, any questions? It should launch in 2018. It's scheduled to launch on Ariane 5, which is a European rocket. Yeah, it's a very collaborative effort, I think. Who's paying for it? James Webb, yeah. I think it's primarily a NASA project, but these days, these huge projects, they involve lots of countries and research institutions like the universities and so forth. I'm not sure where all the dough comes from, but I think it's NASA's budget that's fronting most of the cost of that. But that EELT, I think that's almost completely a European project. Yeah. Yeah, those are, I mean, like that. Yeah, this is, it probably, there was probably some, this image is a Hubble ultra deep field image. They pointed the Hubble at one spot in the sky that's very, very devoid of nearby objects, like stars in our own galaxy, distant galaxies. The blankest part in the sky they can see, and they stare at it for a long time to see the faintest objects they can see at the most distant. So that's what this image comes from, and I don't know where this name may have come from when they did a survey of the image to see what are the faintest objects they can see in it. And that was sort of just the nomenclature by which they named it. Yeah, most of the astronomical objects have these names that don't really look like names. They're just designations on a computer list, So, yeah. Mm-hmm. Mm-hmm. So, some of these sky surveys, really faint, low amount. I guess so. I don't know. Yeah, I suppose they do, but I don't know that. That's a good question. I mean, like this is a nearby star, right? The things when you see the diffraction spikes, that means a point source of light. So this is a nearby object, but these are galaxies, outside the Milky Way. But that must be the case. So that's a good question. I don't know. But yeah, when they have these great big telescopes that come online, I mean, they'll be able to do much deeper versions of this, right? Mm-hmm. Mm-hmm. Yeah, there's no visible light. The radiation. Radiation back here was visible. The universe was smaller and hotter, and it was essentially, that spectrum I showed you, the cosmic background radiation. It's this big, smooth. That's called a black body curve, and it was an almost perfect black body back then, in the visible part of the spectrum. The earlier it is, the higher the frequency. So that would have been extremely luminous. If human had existed back then, it would have been very bright. But as the universe expanded, the whole black body spectrum shifted toward lower and lower frequencies. Now it's way down. A black body spectrum is always associated with a temperature of the emitter, and at this point it was like 6,000 Celsius or something like that, year of recombination. What's the recombination temperature? Something like 6,000 Celsius. Now it's redshifted all the way down to 2.7 Kelvin. So, really cold, right? Way down in the radio part of the spectrum. And so as it was going, as it was expanding here, it was getting more and more infrared. So in this period it was, probably the far infrared. And as you go through time, it's just cooling down to a lower. So there's plenty of radiation, but it was not in the optical anymore. So that's why they call it the cosmic dark ages. If there had been human eyeballs back then, they wouldn't have seen visible light. Oh yeah, this is the cosmic dark ages. Yeah, it's and it's a pretty apt name. But then once the stars started to form, then they were producing, optical and ultraviolet and everything, and it had major effects on the universe when that light was in production again, and has affected the universe ever since. You mean to build that sucker? It'd be a lot easier to build it if there were people there. Yeah. People alive. Right. I mean, it would certainly be a more efficient process if people were there to build it. It would also be more expensive. That's what the discussions I've seen of it, they've talked about doing it robotically. And, right now, it's a very preliminary stage. They've just developed it conceptually. I don't think they've really taken the development of the instruments to any higher level than fairly. I mean, they've built some what do you call it, like preliminary versions of the instruments. There's unfurlable things. Yeah, but until you fund a project like that, which most of the expense would be getting the stuff to the moon. Yeah. Yeah, right. Okay, well, thank you all for coming.